Welcome, everyone. I'm so glad that you can join us for today's webinar. My name is Haley Thomas with PetroSkills, and I'll be your moderator for today. Today's presentation, entitled How to Identify Key Drivers, Benefits, and Drawbacks in Subsea Systems, will be presented by Mr. George Rodenbusch. George is an instructor and consultant for PetroSkills John M. Campbell. He started his career more than 32 years ago and has experience in engineering and management of deepwater offshore oil and gas developments. During the early parts of his career, he worked in R&D where he developed tools for the estimation of loads on offshore platforms induced by wind, wave, and current during severe storms. He then joined a marine systems engineering group, which was formed to develop concepts for the development of deepwater fields in the Gulf of Mexico. Later in his career, he was appointed as Global Technical Expert in Offshore Structure Engineering in recognition of technical expertise and global contribution, and was later named the Global Discipline Head for Offshore Engineering. He holds a bachelor's and master's in mechanical engineering from Rice University and a PhD in oceanographic engineering from Massachusetts Institute of Technology and Woods Hole Oceanographic Institution. George, we're so glad that you could be here with us today. The floor is now yours.
Welcome to today's seminar. I'd like to spend perhaps a half an hour with you discussing some of the key drivers, benefits, and drawbacks of subsea systems. During our session, we have a couple of key learning objectives that we'll address. First is, in fact, the subsea system drivers, and that will be a description of what the main external drivers are that influence the design of subsea systems and the complexity of subsea systems. The second objective of today's seminar is a discussion of the benefits and drawbacks of subsea developments. Why would you consider a subsea development, for instance, since, as we will see, it is generally more expensive per well in terms of a development and more complex. At the end of the session, we'll revisit our learning objectives and see how we did. Let's begin with a little bit of background or foundation with regard to the use of subsea systems. We can begin with the initial style of offshore development, which was essentially to replicate onshore development. And this was done with the use of surface platforms. Thus, you create an area which is similar to a drilling pad offshore in the sense that people can work in the dry. The equipment is very similar to what might be used onshore, and the wells are founded and supported by a platform on the seabed. This style of development requires that you be positioned over or close to hydrocarbon accumulation, so the reservoir needs to be close to your platform. Today's drilling techniques permit a reach or a horizontal extension from the platform location of perhaps 7 miles, although 4 miles is more typical. Thus, the ability of a fixed point surface platform to reach a reservoir is limited by the distance from the location of the platform to the reservoir. These platforms were initially used mostly for the construction and support of the wells, although over time the use of the platform has evolved to include processing of oil and gas. Once you have complex equipment, you need an accommodation, a place for people to live, and additional combinations of these functions are often included on a single platform or frequently a collection of platforms. So creating this infrastructure in shallow water was initially challenging, but became quite common and well developed. Here we see an example of an early offshore platform where we can see structure providing a work area above the seabed. Here we can see on the right a drilling system, and on the left a platform that provided quarters and offices for the people working offshore. And you can see one of the challenges of being offshore, which is that it's remote and requires vessels to provide support for the development. So these offshore platforms are frequently described as providing direct vertical access, DVA access to the wells. So here the wells are not always directly below the platform. The reservoir, as I mentioned earlier, can be a few miles away from the center of the platform, but even a few miles is a relatively small distance given the vast open areas of the ocean. Most, but not all, offshore platforms provide this DVA capability, but they can also just be processing platforms and provide functions for support of pipelines. The DVA units are usually used for production wells. That's wells that produce oil and gas from the reservoir and include the so-called dry trees. So here we come to the point where we can begin to differentiate between the traditional platform development, which was an extension of onshore technology, and the subsea systems that we're going to focus on today. So the key difference between a traditional platform development, dry tree development, is the location of the Christmas tree, the key valves which control the flow of oil and gas from the platform. So the traditional style with dry trees that are visible, relatively easy to maintain, is what we will generally use as a baseline or a comparison for our subsea trees. So for a subsea development, the key aspect is that the trees are located on the seabed, so they're in the water, exposed to the corrosive environment of the sea, and depending on the location, could be very high external pressures due to the water depth. Okay. So beginning in the 80s, there was a move to deeper water, which also influenced the use of subsea systems because the expense of platforms was increasing, and thus the ability to economically develop fields in these new water depths became more of a challenge. So the idea of having a remote or a satellite well that did not require the extra cost of a platform system began to evolve. And these so-called subsea wells, which included wet trees, developed alongside the ability to drill these wells from mobile offshore drilling units, so-called MODUs. These wells were then tied back or connected to existing or possibly new facilities which gathered from several wells, which provide the offshore processing of the produced fluids. The ability to then position these wells independent from the platform became one of the key drivers that made subsea developments attractive and influenced the evolution of the technology associated with subsea systems. So if we can maybe summarize some of those points with regard to the use of direct vertical access or the advantages of direct vertical access. They generally require reservoirs, or attractive when there are reservoirs that require a large number of wells. The cost of drilling a well from a fixed platform is relatively much less than the cost of drilling from a mobile offshore drilling unit. Thus, if you have many wells, the cost of providing the platform offsets the cost of drilling the more expensive subsea well using a mobile drilling unit. Reservoir targets have to be reachable. We mentioned earlier that current drilling technology permits the drilling to a reservoir target up to, say, 7 miles laterally from the location of the platform or the drilling center. More commonly, these reaches are on the order of 4 miles, so relatively small ability to reach distant targets. Thus, the DVA application is only practical or useful when you have the target reservoirs within this drilling radius. Also, the use of direct or vertical access wells is recommended when you have more complex reservoirs that might require more frequent workover or intervention or recompletion. Sometimes you have opportunity to develop multiple reservoirs with a single well. So the dry tree or the non-subsea development is attractive and frequently justified by complexity of the reservoir as well. The one problem that one creates with a remote subsea well is the need to move the production fluids, so the oil and gas that are being produced from the reservoir, to the platform for processing and stabilization. So this challenge is generally described as flow assurance, and the objective of flow assurance is to prevent plugging of the lines that connect the reservoir, the pipes to connect the reservoir to the facility where the oil and gas and water and potentially solids will be separated. So you can imagine that the longer the distances between the reservoir and the processing platform, the more likely one is to encounter problems with the flow assurance problems. So the disadvantages of these fixed platforms or direct vertical access developments is that the cost of the platform is quite high. It can be very high when the development is in deep water, and creates a challenge for economics of a development, in particular if the reservoir is relatively small. So small reservoirs are a big disadvantage. The well positions or the distribution of the reservoir and the location of targets in the reservoir for development need to be compact, and if they are not, which can be the case, then the direct vertical access system is at a disadvantage. The reservoir targets may be difficult to drill. This is perhaps a slight difference from the target location, so there's a limitation on distance, but it can also be influenced by the rock that has to be drilled in order to reach the target objective. It's also possible that distributed accumulations, so one solution for the spatial distribution of the reservoir might be to create multiple drilling locations, and this can be a solution where platform development costs are modest, but in deeper and deeper water, the cost of the platform becomes prohibitive, and those distributed reserves of oil and gas become uneconomical to develop. Disadvantages of the direct vertical axis include the high cost of the platform, which is influenced by deep water or water depth, and can become prohibitively high and make the development of reservoirs uneconomic. The big driver for the cost can often be the locations of the subsea reservoir targets, which can be long distance away, and as we mentioned earlier, if they are at a radius larger than about 4 to 7 miles, not feasible, thus requiring multiple platforms perhaps. The challenges in reaching the reservoir can also reduce the radius of drilling and make the need for more drilling locations and more platforms a technical requirement for development, and thus increase the costs and make the direct vertical axis development a challenge. So here we see a schematic of a subsea development. The key elements of the subsea development are the host platform. In this case, we see a floating platform. A host platform can be floating, but also quite commonly a fixed platform. In the foreground, we see some of the main components of subsea development. The subsea tree, which connects to the reservoir, being the key element of a subsea development, so controls the flow from the reservoir into the subsea system. We see a manifold, which collects flow from several subsea trees and routes them to the host platform through the flow lines, which we can see attached to the system here. Another key component of a subsea system is the control system. We can see an umbilical, which delivers energy and control and chemicals to the subsea system to control flow from the reservoir through the trees, through the manifold, back to the platform, provide some feedback for the platform from the subsea system, including temperature and pressure, the reservoir in the tree, potentially valve locations, positions within the various systems. All of this intended to help ensure the flow in a safe and reliable manner from the reservoir to the platform. What are some of the major subsea drivers? Generally, what we find is that these drivers are responses to some of the disadvantages of our direct vertical axis system. And these might include a response to water depth, where we might be able to save money by positioning our host platform, our production platform, in shallower water by drilling our wells and having our reservoir developed with remote satellites which produce back to the host. In some cases, the reservoirs are located where there might be hazards near the surface directly over the reservoir. So moving the platform, the host system, away from these hazards. It will help ensure the safety and reliability of that development, and is made possible by the subsea satellite system. So another solution, which is again served by the ability of subsea wells to be remotely located, is the access to a very large reservoir or dispersed reservoir. So one can then create wells that are beyond the drilling reach from our host platform, more than, say, 4 to 7 miles away, and develop these large reservoirs. The ability to develop multiple smaller reservoirs, dispersed reservoirs, is also served by the satellite and remote ability of subsea wells. So one can also make use of existing infrastructure. So frequently it's the case that oil and gas reservoirs are discovered close to existing developments, and that the existing developments may be depleted and so have reduced oil and gas production coming to them from the initial development, making it attractive to bring more oil and gas, thus making use of existing facilities, both reducing the cost of the subsea development and continuing to economically use existing offshore systems. So we would like to use subsea systems to reach remote targets, as we've said. Frequently, companies or operators will have a preference for a style of development, which might be the direct vertical access or platform-based or subsea-based. Many reservoirs can be developed economically by either system, and so it's common for a company or an operator to use a system with which they have experience and are comfortable. Use of subsea systems for development is also influenced by the choices that might be driven for the host system itself. A floating production storage and offloading system, an FPSO, is frequently very attractive in remote regions where oil will be directly exported, and the FPSO can only support satellite wells. It's not capable of supporting dry tree DVA wells, and so generally will be associated with subsea systems. So sometimes there are external drivers for selection of the host, which can drive the selection of the tree location. So here we have a simple schematic that illustrates the economic drivers for a subsea system. One axis shows the water depth. The water depth is a big driver here. It generally reflects the cost of the host system. So as we move to the right in this schematic to deeper water, the cost of a platform, DVA platform, becomes high. The reserves, or the amount of oil and gas that can be produced from the reservoir on the left, increases the ability to spend capital and still have profitable or economic development. So the line is a notional balance between the ability of a certain reservoir size to support economic development with a DVA or a fixed platform, which we see requires more reserves as the water depth increases. So the upper left-hand corner is the economic area, thus you have enough oil and gas to offset the cost of development and the cost of operation of the platform and can be developed. The lower right-hand corner generally is not economical for development. With the fixed platform, the costs are too high and the amount of oil and gas that can be produced from the reservoir insufficient to offset those costs. Here the star shows the reservoir or opportunity that we might have, and so in this case we see relatively deep water, relatively small reserves. So notionally, a reservoir that cannot be developed with a DVA direct vertical access platform. So with the use of subsea systems, we can move the economic development for that reservoir to by the use potentially of a platform in shallower water, thus reducing the cost of the capital and making the development of a small reservoir reasonable and attractive. We could also have a host potentially in the similar water depth as our target prospect, and yet by tying back multiple prospects to the host, create a collection of developments which together are economic, no one of which could have supported a direct vertical access platform or a host platform. Thus, by being able to increase the radius of reach beyond what is currently feasible with drilling, we can make a small reservoir economically attractive. So, benefits of subsea we've talked about already. We can summarize here. We can avoid the cost of a surface platform. Now, this is not entirely true. A subsea system requires a host of some sort. A host can be a fixed platform or a floating platform, or in fact the subsea system can be managed from onshore. And so there is some cost that must be supported by the subsea development. However, the subsea system does not necessarily bear the entire cost of that development. As we mentioned before, it's possible to tie back to existing infrastructure or possibly develop multiple subsea or multiple reservoirs with subsea systems back to a single platform and thus share the benefits. So perhaps reduce the cost of the surface processing and host platform. The attraction of subsea might also be to accelerate production. Generally, the development of a large host platform may take 3 to 5 years, and the production of the reservoir must then be delayed until that host platform is in place. Frequently, the wells that would be drilled from the host platform then require additional delay before production of the oil and gas. A small subsea development can be delivered in a time frame of 2 to 3 years, and thus if you are tying back, for instance, to an existing facility, one can get production of that reservoir accelerated. We've touched on well placement, So this reflects the limited ability of existing systems to reach more than, say, 4 to 7 miles from the drilling center, and thus a subsea system permits the wider distribution of wells from a host or from a single drilling center. This might provide more flexibility in terms of the trajectories of wells, which might be positioned potentially to penetrate multiple producing horizons in a reservoir. Can also avoid drilling hazards, as we mentioned earlier, hazards related perhaps to the platform location on the surface. It's also possible to potentially avoid zones that are unattractive from a drilling perspective and might be more likely to cause drilling problems. The Subsea Development also provides flexibility with how one invests capital, and this is a function of the cost of the host generally. So one must make a large investment in the host in order to support the maximum number of wells, let's say, that one wants to eventually drill, and thus increases the size of a platform. For a subsea system, one can develop a system which is easily expandable and thus begin with a relatively small number of wells, minimizing the investment of capital initially, which can be attractive if the reservoir is not as large as hoped, but also can permit the phasing of capital investment over time, starting with a few wells that then begin to provide income, which can then be used to continue development of the field. Already mentioned the idea of starting with a small number of wells to test a field. One of the main drawbacks in developing with a subsea system is flow assurance risk. So the long distances which make a subsea system satellite attractive also create a hazard or hazards potentially with regard to flow assurance or plugging of the flow lines that are bringing production to the platform. So this flow assurance risk then generally requires investment in the system, solutions including multiple flow lines that permit pigging or cleaning of the pipeline systems, as well as use of chemicals which are inhibiting problems, potential problems such as hydrate formation or wax formation, thus require systems for delivery of those chemicals, injection into the flow system, and increase the cost of the subsea system. Lower economic reserve recoveries are a drawback of subsea systems. The long offset of the subsea system from the producing platform increases the back pressure on the reservoir and thus reduces the ability to produce oil and gas from a given reservoir system. The cost of intervention is also high in that subsea systems are remote and require specialized systems for maintenance of the subsea equipment, and also expensive mobile drilling units for maintenance and intervention in the wells. thus the ability to pay for the rehabilitation of a well with relatively small production is reduced for subsea wells, and consequently reserves that might notionally be recoverable from a direct vertical access system have to be abandoned with a subsea system. The high system reliability is a consequence of the expense of intervention for a subsea system, thus balancing the cost of having frequent failures and requiring expensive intervention with the higher initial cost of guaranteeing high system reliability. The lack of the simple direct vertical access is reflected in these costly well interventions, costly system interventions, and the high initial drilling investment if wells are drilled with a mobile drilling unit. The higher overall development risk is a consequence of the increased complexity of the system. You have more components, more sophisticated components required for a subsea system because of the remote nature of the development, as well as the more challenging environment in which that equipment has to operate. That is, operating in the water under high pressure due to the water overhead, as compared to having that same functionality on a platform in the air where it's more easily accessible and more easy for people to maintain and intervene. So subsea systems can generally be classified into two groups. One group is characterized by a complete system development that includes the host, which will provide the processing for the oil and gas, as well as provide a place for people to live and work in order to operate the subsea system. So this then provides the opportunity to have all of the subsea system support requirements incorporated in the initial design of the host. The second general group of subsea developments is the so-called subsea tieback to an existing host. So in this case, the existing host, if it's a modern host, may have the necessary interfaces planned for a future tieback, in which case the development is more straightforward than for the alternative, which would be a tieback to a host where subsea systems were not expected and thus require modifications to that host with the consequent costs required to provide the interface with the subsea system. So subsea system complexity is driven, as we've seen, by the remoteness of the equipment, as well as the need to have mobile units for drilling, and the need to have an interface with the equipment that is generally on the surface and may be thousands of feet, miles, kilometers away from the equipment that is providing support. So this complexity is often driven by the installation needs and a number of components that are used in order to make it possible to assemble the system on the seabed. Listed here are pipeline end terminations, manifolds, the umbilical termination assembly, subsea distribution units and such that are components that allow the interconnection of trees and manifolds and pipelines and umbilicals on the seabed. Complexity is driven by component installation in the water. Some of the challenges are listed here. It's not possible to see in water depth over 300 feet or 100 meters where there is no light, so you have to bring your own light. People require protection. Divers, in fact, can only work at depths up to perhaps 300 meters, and that's such a hazardous activity that it's avoided as much as possible. So special equipment is required in order to be able to manipulate the components at depth, and cameras required to be able to see, and lights required to be able to see. The distances are quite large, so all of this is done with remote systems that have to work on the surface of the ocean, which generally can be moving in waves and currents, complicating the installation. And these components are heavy and require installation support vessels that can be quite expensive to use, thus increasing the overall cost of the development. So frequently the complexity of a subsea system is increased in order to reduce the size of the vessel and the cost of the vessel and help optimize the overall installation. Yeah, they have to operate at high external pressures, which can be a challenge for the integrity of all of the connection systems, and in particular the use of electronic systems for control and monitoring of the subsea development. The subsea wells can be used for the same general applications as surface wells. We've mostly focused on production wells so far. They're also used for water injection wells, which may be used to dispose of produced water, or possibly for reservoir pressure support in order to enhance production, and also used for gas injection wells, which may be used to sequester gas, or possibly also used to maintain pressure in existing reservoirs. In the first bullet there, we have listed a few of the subsea processing systems that are occasionally desirable and associated with production wells. This might include the separation of oil and gas and water, which may have an advantage from the perspective of improving flow to the platform, and possibly also improve the flow assurance. Pumping is a way of adding energy to the production from the well, and therefore improving the recovery from the reservoir. And that's complemented by compression, which helps improve the production from gas reservoir by reducing the pressure at the subsea system and moving the hydrocarbons to the production host. So that brings us to the close of our discussion of some of the key system drivers for subsea systems, as well as the benefits and drawbacks of subsea systems. As we've seen, some of those key drivers include the reservoir distribution, the reservoir size, so widely spaced reservoirs, small reservoirs make subsea more attractive because it can bring those reservoirs back to a facility which is shared with other developments, possibly subsea or DVA as well, and can also be used to tie back distant reservoirs to existing infrastructure, thus reducing the overall cost of producing those reserves and improve the economics of these fields. Some of the drawbacks of subsea system include the potential for flow assurance problems because the long transportation distances between the subsea system and the host, and the need to avoid the formation of plugs in those systems, in those transportation systems pipelines. The system is also made complex by the distance from the surface, the remoteness of the components, and the requirement to operate those remotely and to have the ability to gather data from the reservoir and from the subsea equipment for use in managing the reservoir.
Okay, thanks so much, George, for taking the time to present this webinar for us today. The topics discussed are also covered in our Fundamentals of Subsea Systems SS2 course. Other courses that the participants may be interested in also include Overview of Offshore Systems and our Fundamentals of Offshore Systems Design and Construction course. Thanks again, George, and to all of our participants, and we look forward to seeing you in one of our upcoming PetroSkills John M. Campbell training courses.